Hey guys, in this video we're going to talk about Chapter 12, Section 2, Graphs and Surfaces. So what is a graph in 3 dimensions? So we talked about finding points in 3 dimensions last time based on an equation. And so by definition, the graph of a function of 2 variables is the set of all such points that satisfy an equation in 3D. Okay? In general, the graph of a function of 2 variables is called a surface in 3 space. All right, so let's go ahead and look at an example of a graph in 3 space or in 3D. Sketch a few points on the graph z equals x squared plus y squared, and then let's examine the surface that all of the points that satisfy this equation make using GeoGebra. So I'm just going to sketch a few points. So let's sketch a few points. Let's just set x and y and figure out what z is. So if we set x equals to 0, y equals to 1, to solve for z, we just plug in these guys. I have to pick 2 points as my input, remember, and we get 0 squared plus 1 squared. So that's going to give us a z equals 1. And so here's 1 point on the plane, or not on the plane, on the graph, I'm sorry. Another point, we could say, okay, well, I'm just making up things here. I could say, well, how about our input is x equals 1, y equals 0. Well, in that case, we have z is going to be equal to 1 squared plus 0 squared. Again, z is going to equal 1. Okay, so that's another point on our graph. And then we could do x equals 1, y equals 1 as our inputs to figure out what our output z is going to be. So we have z equals 1 squared plus 1 squared. So z is equal to 2. All right, so that's another point. So we can write all 3 of these points as ordered pairs. Right, we can say this one is x is 0, y is 1, z is 1. This one could be x1, y0, z1. And this one is x is 1, y is 1, z is 2. So there are an infinitely many points on this graph that will satisfy this equation, but these are just 3 points that are actually on the graph. Now let's see what happens when we plug z equals x squared plus y squared into GeoGebra. Alright, so in red is my function z equals x squared plus y squared, and then I've plotted the points that we found, and you can see those guys actually lie on this graph in blue. Now, of course, as I mentioned, there are infinitely many points that are going to satisfy the equation z equals x squared plus y squared, but this is the shape that we get. And notice that it looks like a parabola. It looks like a bowl. And what we call this, so we call this surface, and we're going to get more into why we call it this. We call this surface a paraboloid. Basically, it's the 3D version of a parabola. All right? So let's talk about a special type of graph, and that's called a cylinder. Now, typically, when you guys think of a cylinder, you probably think of something that looks like this. And in calculus, or when we're plotting 3-dimensional figures, a cylinder doesn't necessarily have to look like that, but it has to illustrate a similar idea. What do I mean by that? Well, notice that in the cylinder that we're used to, basically, we have circles that are projecting upwards. Okay, so we have circles that are projecting upwards like this. Okay, so that's a cylinder. Because we're basically taking a base circle and just projecting it up, right? Along the z-axis in this case. Now, we could also have a cylinder that looks something like this. So we could have maybe a half cylinder that looks like that. So what I'm trying to get at is that, you know, in the regular cylinder that we're used to, we're projecting a circle upwards, but we could really project any shape that we wanted. We could project half of a circle upwards. We could, you know, project a triangle upwards. That would be considered a cylinder. Something like if we had maybe like this, and we just projected it upwards so that little triangles, oops, you guys can see, I have to work at my artistic drawings. Okay, so we could have something like this. This would be considered a cylinder because we're imagining triangles being projected upwards along the z-axis. And you may have seen these already in geometry called prisms. That's what they're called, prisms. So let's look at what these cylinders mean algebraically and geometrically. Alright, so our first example, sketch the graph of the surface z equals x squared. Now the first thing I want you to notice is which variable is missing. The variable that's missing is where we're going to project the surface. Okay, so we are going to, since the y variable is missing, we are going to project along the y-axis. And another way to read the z equals x squared, another way to think about z equals x squared. What this means, since y is not involved, right? Y is not involved at all. We can say the following. We can say y can be anything, but z is equal to x squared. All right, so let's go ahead and graph this guy. Y equals z squared. Let me go ahead and draw my 3D plane right here. Okay, so this is my x, z, and y. And maybe we can extend the x out a little bit like that. Okay, so remember the graph y equals x squared. We all know what this looks like. In algebra, we graphed it. We had the x-axis right here and the y-axis right here, and this is what our picture looked like. Now, for z equals x squared, you just want to use this picture to construct your graph, right? X equals z z equals x squared. The only difference is that now, instead of the y-axis being vertical, the z-axis is vertical. So z equals x squared just looks like this, and we can graph this on our plane right here. So it's kind of going back like that. You can imagine that, and then it's going to, we're projecting it along the y-axis because y is missing. And so what that means is that we're going to draw parallel lines from our parabola projecting along the y-axis, so parallel to the y-axis. Just going to pick random points on this parabola. Maybe we'll do the vertex as well. So y can be anything we want. However, z equals x squared. So I'm just going to project this like so. Okay, so you see how I projected the parabola in the back to the parabola in the front. So there's infinitely many of these that I just didn't draw, but I could if I wanted to. Okay, there's a parabola there. All right, so anyway, this is a cylinder because we are projecting a parabola along the y-axis, right? Y can be anything. Y can be anything. Notice that y could be right here. This goes out as far as we want this way and as far as we want this way because we're projecting this graph z equals x squared along the y-axis. That is a cylinder. That's the idea of a cylinder. And it's not a circle, right? It's not a circle like we would normally see a cylinder being drawn, but it's the same idea. With a regular cylinder, we're projecting a circle along the z-axis. With this cylinder, we're projecting a parabola along the y-axis. All right, so let's go ahead and do another example. All right, sketch the surface x squared plus y squared equals 1. First thing I want you to do, identify the missing variable. Z is missing. So we're projecting along the z-axis. And another way to think about this is z can be anything, since we're projecting along the z-axis. However, but x squared plus y squared equals 1, okay? Now, you should recognize this as the equation of a circle. So the equation of a circle with radius 1. Okay, this is the equation of a circle with radius 1. And just a basic equation of a circle centered at the origin. Maybe I'll write this down just so you guys have a refresher. So a circle centered at the origin with radius r is x squared plus y squared equals r squared. It's the equation of a circle, and we can see in our case, our radius of a circle is 1. So what this is a classic cylinder that you're used to seeing. This is a classic cylinder that you're used to seeing. So here is our z-axis, our x, and our y. And if we start at 0, right? If we start at 0, at z equals 0, z can be anything but x squared plus y squared equals 1. Well, how do we draw x squared plus y squared equals 1 in the xy plane? It's just, again, it's just a circle like this with a radius of 1. Okay, so that's what we're going to try to do right here. I'm going to try to draw this circle like so. Okay, so that's when z equals 0. And then we're just going to project this thing up. Just going to draw some parallel lines to the z-axis to project my circle up. And so you get your projected circle up here. And remember that there's z can be anything, so there's infinitely many circles being projected upwards. I'm just drawing a few here just to get the point across, but this is our classic cylinder. These red circles represent x squared plus y squared equals 1. Z can be anything. And yeah, so that's what it looks like. All right, what about something like this? So what's your missing variable here? Your missing variable is x. So x can be anything. but y squared plus z squared is equal to 1. So this is still a circle with radius 1, but now, because x can be anything, we're projecting this thing along the x-axis. Okay, so here's my z, my x, and my y. So y squared plus z squared. So now we're plotting in the yz plane. And so the idea here is that, you know, we're traveling along the x-axis, and the circle that we're making is going to have a radius. This circle right here is going to have a radius of 1. Once again. And basically we're just projecting this thing. Let me see if I can draw this a little bit better. Okay. And we're projecting this thing along the x-axis. Okay, so at the end of this, I'm going to get another circle like this. And keep in mind that all, you know, going along the x-axis, we have infinitely many circles, and it extends off into this direction as well. Okay, and I know I'm not the best artist, so let's go ahead and take a look at this in GeoGebra. Y squared plus z squared equals 1. That's a better picture. So as we can see here, our circle is plotted in the YZ plane, and it's projected along the x-axis, that red axis, and that's kind of what I was going for here, but as we can see, it wasn't the best rendering. So that should have been more curved like that. But yeah, that's the idea here. So it's kind of like a sideways cylinder going along the x-axis. Alright, so find the equation of a cylinder of radius 2 with its axis along the x-axis. So again, what this means is that x will be missing in our equation. And so what is a cylinder? Well, a cylinder is just a circle projected along an axis. Since x is missing, the only variables left are y and z. So we have y squared plus z squared is equal to the radius, which is square root of 2, squared. So this is just going to be y squared plus z squared equals 2 when I square that square root. So that is our equation of the cylinder, with radius root 2, and its axis is along the x-axis. Okay, so let's sketch the surface. Z equals x squared plus y squared. Now this guy isn't a cylinder because all of our variables are present. So in order for it to be a cylinder, in order for us to project a shape, a curve along an axis, we have to have 2 variables, and that's it. All right, but we have 3 variables here, okay? So our picture might look a little bit different. And you might be asking, well, how do you sketch something like this? Well, you know, it helps to fix our variables. Let me show you what I mean by that. So fix the variables. So let's look at first fixing the x value. And what I mean by that is just picking a number for x, plugging it into this equation, and getting out an equation in the yz plane. Okay, so let me actually put this in parentheses. We're going to get an equation in the yz plane. All right, so let's just pick some random numbers for x. How about x equals 0? So if x equals 0 in this equation right here, we get z is equal to 0 squared plus y squared, which is just z equals y squared. Okay, so when x equals 0, z is equal to y squared. So let's just put that in our pocket for a second. And what I want to do is I want to just show you what this looks like on the graph. And imagine that that your y is right here and your z is right here. So we're plotting on the yz plane. And this guy is just a parabola, right? At x equals 0, we have this guy right here. Just a little basic sketch for you. Let's choose some other x values. How about when x equals 1? What do we get? Well, when x equals 1, if I plug 1 into this equation up here, I get z is equal to 1 squared plus y squared, which is just 1 plus y squared. So z equals 1 plus y squared, or y squared plus 1 is a better way to write that. And we can see here that this is just a parabola shifted up 1 unit. So it's going to look something like this. Okay. All right. Let's do one more. Let's do x equals 2. So when x equals 2, we get z is equal to 2 squared is 4 plus y squared. So y squared plus 4. So it's just a parabola shifted up 4 units. So maybe it looks something like this. Okay. So that is the view of our 3D object in the YZ plane. Okay. Let's try seeing what happens in the XZ plane. So let's go ahead and fix Y. So when we fix Y, we're looking at this in the perspective of the XZ plane. All right. So let's go ahead and fix some values. So let's fix y equals 0. And if I fix y equals 0 in this equation up here, I get z equals x squared plus 0 squared. So that's just z equals x squared, another parabola. So this time I am graphing from a different perspective. I'm now looking at the XZ plane. All right, so here is my first parabola right there. And we're going to get a similar story for the other ones. When y equals 0, we get z is equal to x squared plus 1. And when y equals 2, we get z is equal to 2 squared plus 1. I'm sorry, not 2 squared plus 1. X squared plus 2 squared, which is plus 4. All right, so now we have this. So basically what these, we call these traces, these little, you can call them traces, you can call them cross sections. But basically what these are telling me is that no matter which side I'm looking at the shape from, the sides of it are going to be parabolas, okay? Basically, like you're going to have a bowl shape. Imagine wrapping this all the way around, like 360. You're going to get a bowl shape. So no matter how we look at it, we're going to be looking at the shape of a parabola. Now, what happens if we fix z? if we fix z, we're getting an equation in the xy plane, so we're looking down. In xy plane. So when we fix z, let's say that z is equal to 0. Well, then we get 0 is equal to x squared plus y squared. So that's just a point at the origin, a radius 0, a circle with radius 0. When z equals 1, we get 1 equals x squared plus y squared. When z equals 2, we get 2 equals x squared plus y squared. So as we're getting higher and higher, the radius of our circle is getting bigger and bigger, right? As we get higher and higher in z, the radius of the circle is getting bigger and bigger. So let's go ahead and just kind of sketch what this looks like. So we're in the xy plane, and x squared plus y squared equals 0 is that. X squared plus y squared equals 1 is a circle radius 1. X squared plus y squared equals 2 is a circle of radius 2. So as we're moving up, so as we move up in the z direction, our circles get bigger. So putting this all together, we can give a little bit of a sketch about of how this would look like without using GeoGebra. So let's do my xy plane with z perpendicular. All right, so here is the point 0, 0, 0. This is z, this is my x, and this is y. And so what I'm going to get, I'm going to get sort of this bowl shape, right? So I'm going to get something that looks like this. So notice that as I'm increasing in z, my circles are getting bigger. Okay, you can see that as I'm going up in z. And then also notice that however you look at this thing, you're going to see a parabola in the trace. So like this guy would be our parabola in the xz plane. And then maybe you can draw one in a different color, purple, and maybe it looks something like this. Okay, so those are our parabolas in different perspectives. Again, the circles are representing my circles in the xy plane, and they're getting bigger as we go up in the z coordinate. Now you can always check GeoGebra to make sure that your picture is accurate, because some of these pictures are tricky to draw, but I do want you to kind of practice seeing what these look like from different perspectives, because it's going to help you a lot later on when we're doing the actual calculus. So anyway, let's put this in GeoGebra just to confirm our picture. So we have z is equal to x squared plus y squared. And there it is, guys. There is our paraboloid. Okay? And notice that you can shift perspectives, right? So the first perspective that we looked at was the equation in the YZ plane, and we saw those were parabolas. So if we look in the YZ plane, that is the green and blue, okay? Just imagine like that's our picture. We can see the parabolas, right? If we look in the XZ plane, again, if we shift it like this so that Y is irrelevant, we can see the parabola there. So that's the idea. And if we look from up and down, we can see the circles, and the radius of the circle gets bigger as we move up. Okay. All right. So let f of x, y equal x squared plus y squared. Describe in words the graphs of the following functions. Now, f of x comma y is just another notation for z. So this is z equals x squared plus y squared, and you want to recognize this as a paraboloid. You want to say right off the bat, this is a paraboloid. And so the idea here is that these things in 3D behave just like they do in 2D. For instance, if I gave you a parabola y equals x squared, and then I said, well, what about y equals x squared plus 3? What would happen? Well, what would happen is that it would just shift up 3 units, right? And so that's the idea here. We are given the basic paraboloid here, centered at the origin, but this time it's shifted up 3 units. Okay, so this is a paraboloid centered at origin, shifted up 3 units. That's the basic idea. Now what about the next one? Okay, well, this time we have negatives on our inputs. What happened if we had something like this, y equals negative x squared? What would happen there? Well, remember, it would flip the direction of the parabola, so that would be opening downward instead of upward like this. So that's the idea here, is that our bowl shape, our paraboloid, is going to be facing downward. And this 5 is still acting like a vertical shift. It's going to shift it up 5 units. So this is paraboloid opening down, shifted up 5 units. Still centered at the origin. And you should confirm all of these on GeoGebra. Okay, and the last one is this guy. So remember when we had something in college algebra like y equals x minus 1 squared. What did that mean? Well, that just said, hey, pick up x squared and move it to the right 1 unit. So it looks something like this. We moved it to the right 1 unit. So that's what we're going to do here. We're just shifting to the right in the y direction 1 unit. So this is just an easier way of saying this is that the vertex is shifted in the y direction. So this is a paraboloid with vertex at x equals 0 and y equals 1. Okay? Alright, describe the cross sections of g of x comma y equals x squared minus y squared with y fixed and then x fixed. Use these cross sections to describe the graph of g. Okay, so let's go ahead and, as I said, cross sections and trace can be used interchangeably. So the first thing we're going to look at is y fixed. So when y is fixed, we're concentrating on what's left, the xz plane. Okay, so we want to go ahead and put our z up top, x right here. Now when y is fixed, let's choose y equals 0, y equals 1, and y equals 2. So when y equals 0, if I plug in 0 for y up here, I just get z, which is g of x comma y, equals x squared. When y equals 1, I get z is equal to x squared minus 1. When y equals 2, I get z is equal to x squared minus 4. So I can graph all of these guys. I have this guy right here, just my basic parabola, z equals x squared. Then I have a shift down 1 unit. So this is going to be x squared minus 1. So it's going to look something like that. And then I'm shifting down 4 units for this last one, so maybe something like that. Okay, so that is my my xz trace. All right, now let's look at when x is fixed. So when x is fixed, we're looking at what remains, the yz plane. Okay, so when x is fixed, let's choose x to be 0. You could choose x to be anything. It doesn't have to be 0, 1, 2, just a fixed number. When we plug 0 in for x into this equation right here, we have 0 minus y squared, which is minus y squared. So z equals minus y squared. When x is equal to 1, we get z is equal to 1 minus y squared. And when x is equal to 2, we get z is equal to 4 minus y squared. Let's go ahead and graph these guys on the yz plane. So here's my z, here's my y. First one is negative y squared, so this is parabola opening downward, like that. Then we have negative y squared plus 1. So that's opening downward but shifted up 1 unit. This maybe looks like this. And then we have z equals 4 minus y squared. So again, opening downward because of that negative 1 in front of y squared, but it's shifted up 4 units. Okay, so that's from the perspective of the yz plane. That's what this looks like. And then, yeah, so what we're expecting to see in this graph, and I'm not going to draw this because it's going to look a little bit messy, but what we expect to see when we're looking directly at the yz plane are parabolas like this. When we're looking directly at the xz plane, we're seeing upward parabolas like that. And what's happening when we fix z? Well, you guys can play around with that, what happens when we fix z. But for now, I want to show you that these traces do actually match up with the graph that GeoGebra is going to give us. So z equals x squared minus y squared. Let's delete this. Alright, so there's our picture. Let me get rid of this paraboloid up here. Delete that. Okay. Alright, so this is our picture. Let me try to zoom out a little bit. There we go. Move it around. Okay. Alright, so let me see if I can mess around with it. Let's see. Okay, that's a better picture. Okay, so let's first look at when y was fixed, when we're looking directly at the xz plane. So the xz plane, we make x positive. So the xz plane is right here. You guys can see it. X is positive in the red, y is positive on the blue, and you can see the trace of our parabolas, hopefully, in this plane. Now, if we shift over to when x is fixed, that's going to be the yz plane. So let me rotate this guy. So now we're in the yz plane, and we can see those downward facing parabolas. So this is something that's called a saddle. Okay, so this is a saddle. Alright, so let's sketch the surface with the given equation. So the first thing that we need to know is, to do this, is the equation of an ellipse. So an ellipse is oval shaped. It's basically the shape of an oval. And it has the following form. So x squared over a squared plus y squared over b squared is equal to 1. And it's going to look something like this. Something like an oval. And along the x-axis, the length from the center of the ellipse to the edge is going to be a. And then from the center to the other edge is going to be a. So altogether, that length is 2a. And then same idea on the along the y-axis. This length is going to be b, and this length right here is going to be b. So that total length is going to be 2b. Okay, so let's put this away for now in our memory. And the first thing I want to do to get some good points is one other way to get some good points here is to find the intercepts. So for the x-intercepts, this occurs when y is 0 and z is 0. So if I take this equation up here, plug in y is 0 and z is 0, I get x squared plus 0 squared over 9 plus 0 squared over 4 equals 1. These go to 0, x squared equals 1. Take the square root of both sides, and I get my x-intercepts are plus and minus 1. Okay, so I'll just go ahead and draw that real quick. So z, y, x. So my x-intercepts, we have -1 here, and positive 1's maybe right there. Okay, let's do the y-intercepts next. So for my y-intercepts, this time x and z are 0. So I have 0 squared plus y squared over 9 plus 0 squared over 4 equals 1. And I'm going to solve for y. So this clears. Multiply both sides by 9 to get y squared equals 9. Take the square root of both sides to get y is plus or minus 3. So those are my y-intercepts. So I have, let's see, 1, 2, 3, and then I'll go out this way as well. 1, 2, 3. Maybe I'll just not make it dotted. Alright, so I have -3 over here, +3 over here. And finally, I'll get my z-intercepts by setting x and y to 0. Okay, so when I do that, when x is 0 and y is 0, these clear, and I'm just left with z squared over 4 equals 1. Multiply both sides by 4 to get z squared equals 4, and square root to get z is equal to plus or minus 2. So those are my z-intercepts. So I have, let's see, 1, 2 could be right here. And then if I go down, 1, 2 would be right here. Alright, so those are all of my intercepts. Now let's look at this in perspective and talk about what this looks like in the xz plane, the yz plane, and the xy plane. And to do that, remember, we have to fix values. So let me go ahead and erase some of this. Erase some of that. Okay. So let's see what happens when we're looking at the YZ plane. Okay. So the YZ plane. And this occurs, not x, this occurs when x is 0. Okay, so when x is 0, if I plug 0 into x into this equation, I get y squared over 9 plus z squared over 4 equals 1. And I can compare this to this equation and say, oh, well, that's going to be an ellipse in the YZ plane. So let's go ahead and graph that out. Let's see. So in my YZ plane, I have the y value, like the length is going to be 6, right? It's going to be 2 times a in the y direction, or 2 times b if you like that. And then in the z direction, I have a radius of 2. So it's going to look something like this. Something like this. my YZ plane. Okay, so that's my ellipse. You can see that Z is associated with a B value of 2, right? Because it's 2 units. 2 squared is 4. And then our A value is 3, and that makes sense because along the y-axis, this goes out 3 units here from the center, this goes out 3 units, okay? So that's my trace along the YZ plane. Now let's take a look at what's happening in the XZ plane. So in the XZ plane, that occurs when y is 0. And so what we have is just plugging in y is 0 in here. We have x squared. This clears to 0, of course. So we get x squared plus z squared over 4 equals 1. And notice that x squared is understood to be over a 1. So again, we have an ellipse. Compare these formulas. So let's go ahead and trace that out in the XZ plane. So that's going to be kind of like this. In the XZ plane. So there is my ellipse right there. And finally, let's take a look at what is happening in the XY plane. That occurs when z is equal to 0. So when z equals 0, this clears, and I'm just left with x squared plus y squared over 9 equals 1. Keep in mind this is over 1. So again, we have an ellipse in the xy plane. In the x direction, we have a radius of 1. In the y direction, we have a radius of 3, right? 3 squared is 9. So let's go ahead and just trace that out. So that's gonna, we're connecting the x and the y's. So that's gonna be something like this. All right, so we have ellipses all along our traces, and we call this 3D thing an ellipsoid. All right, so I want to talk about planes a little bit more, and we're going to continue to talk about planes in coming sections, but I want to talk about the general form of a plane. We looked at special types of planes. In particular, we looked at the XY plane, the YZ plane, and the XZ plane, and then we just looked at planes that were parallel to the XY plane, so like z equals 4 was parallel to the XY plane, and then, we looked at planes parallel to the XZ plane and the YZ plane as well. But this is the general form of a plane. Of course, A, B, C, and D are going to be numbers. So let's take a look at how we can graph a plane. So the first thing you should recognize is, yes, this is a plane because the variables aren't squared, and this f of x comma y can actually be written as z equals 1 plus x minus y. So you can, this is the same form as this, right? In our case, A is 1, B is negative 1, C is 1, right? Well, actually, C is going to actually be negative 1 if we move that over, if we move the Z over to the right side so that's equal to 0. So C is going to be negative 1, and D is going to be positive 1, okay? So yes, this is a plane for sure. And let's talk about how we can graph this. Again, what I like to do is I like to graph the intercepts. This is going to give me a really nice picture of the plane. So let's first look at our x-intercepts. So this occurs when y and z are 0. Okay, so if I plug in 0 for z and 0 for y and solve for x, I get 0 equals 1 plus x minus 0 is just 1 plus x. Subtract 1 from both sides and get x equals negative 1. So my x-intercept is going to be x equals -1. This is going to lie on my x-axis. And let's go ahead and find the other intercepts as well. Let's do our y-intercept. So this occurs when x equals z equals 0, right? X and z are both 0. And so, again, we're just plugging in those conditions into our equation above. Solve for y, 0 equals 1 minus y, add y to both sides to get y equals 1. So my y-intercept is going to be y equals 1. And finally, let's do the z-intercept. The z-intercept is going to occur when x and y are 0. So my z-intercept is going to occur when x equals y equals 0. Again, just plugging in 0 for x and y into my plane equation. I get z is equal to 1 plus 0 minus 0, so z is just equal to 1. Okay, so that is my z-intercept. And that's all we need to graph a plane. So let's go ahead and sketch a graph of it. And so we have our z, y, x. And then we'll go like that. Okay, so x is equal to -1. That's going to be over here. No, that's the positive direction, I'm sorry. It's going to be back here. Then we have y is equal to 1, so that's going to be right here. Z is equal to 1, and that's going to be up here. And then we just connect the dots and makes a little triangle. Now, if you want to actually see the plane, you can just extend these points outwards, and so it's going to look something like that. Extend that like that, and extend that like that. Okay, so that's kind of a rough sketch of our plane. Let me just shade in our plane here. Okay, so that's our plane. Let's go ahead and do one more example. So again, this is a plane. I have x's, y's, z's, nothing's squared, nothing's cubed. This is a plane. Let's go ahead and find our intercepts. So for my x-intercept, I'm going to let y and z equal 0 in this equation. So I have 2x plus 0 minus 3 equals 0. Add 3 to both sides, 2x equals 3. Divide both sides by 2 to get x equals 3 over 2, which is 1.5. So my x-intercept is going to be 1.5. My y-intercept, x and z are both 0. And so I'm just going to plug those values in there. So I have 2 times 0 plus y plus 2 times 0 minus 3 equals 0. That goes to 0. This goes to 0. Add 3 to both sides to get y equals 3. So my y-intercept is going to be 3. And finally, my z-intercept occurs when x and y are 0. So x equals y equals 0. Subbing those values into our equation, we get 2 times 0 plus 0 plus 2z minus 3 equals 0. That goes to 0. Add 3 to both sides. 2z equals 3. Divide both sides by 2, and we get z equals 3 over 2, or 1.5. So our z-intercept is going to be 1.5, and now we can graph our plane. So let's go ahead and do a quick sketch here. Alright, so x-intercept is 1.5. So I'm going to make that right here in between 1 and 2. Y-intercept is 3, so 1, 2, 3, looks like that. And our z-intercept is 1.5, so we have 1, 2, 1.5 is going to be in the middle right there. And then we just connect our points. We have this guy, and this guy, which makes part of our plane. We can go ahead and extend the plane outward like this. Sorry, let's make that a little bit straighter, like this. Let's shade it in. So there is our plane. This little triangle section is just part of it. And keep in mind, guys, these planes are infinitely thin, and they go out infinitely in each direction, okay?